Thanks everybody for coming for our OMFIT step tutorial. Today we're going to hear from Tim and Joey. I'm going to give a brief introduction about step before they show us things in live. So super quickly, just a reminder of what is STEP. STEP is this module in OMFIT that couples stability, transport, equilibrium, and pedestal, from which we have the name. You can use this for many different applications, but specifically, it really works well for predicting tokamak scenarios. So the way STEP works is that we have all of the physics codes that you see here on the right, kind of grouped by topical area. Those are the physics code that we all know and love, and each one of those is wrapped into what we call a step, which effectively reads data from a centralized data structure and does its calculation and then writes the data back into the same data structure. And the advantage of this approach is that each one of these steps are interchangeable and allow us to perform a variety of workflows. These workflows can be open loop, so given some plasma parameters, given some actuator parameters, what my plasma looks like. They can be closed loop, you know, I want to achieve a certain plasma, how do I get there? Or they could be some optimization workflows, so what parameters maximize a desired plasma metric. And I should really point out that the centerpiece of STEP is this IMAS data structure, which adopts the organization specified by the IMAS data structure. We'll talk more about that later. So just to guide you through what you're going to see today. So Tim is going to talk about some D3d Scenario Exploration. So in his part of the tutorial, he's going to start from an existing TRASP analysis, and he's going to run 3 simulations. The first simulation would be based on the experimental conditions of the experimental run. And this is important to kind of verify that STEP can reproduce reasonably well the experimental conditions. And then he's gonna make some exploration off of the experimental conditions, running 2 simulations at different magnetic field, one at 2 and 2.5 Teslas. And instead of using just 2 megawatts of power, which is what is the experimental setup, he's going to increase the neutral beam power to 12 megawatts co and 2 megawatts counter. In his workflow, he's going to step through the cheese module for equilibrium, chef for the heating and current drive. 1.2 is going to evaluate the current evolution, and Tijaro the evolution of the kinetic profiles. For Joey's part of the tutorial, instead he's going to do a reactor study starting from some 0D parameters. He's going to use the Procreate module, which will generate the equilibrium and some plausible H-mode profiles and some Gaussian heating profiles based on these 0D parameters. And then he's going to step again through the same components to give us some self-consistent reactor simulation and give us a prediction of the fusion power. What I will do is I will actually start setting up the step module in OMFIT. I'll talk about how the module is organized, and then Tim is going to take it away from there. So to start OMFIT on Iris, we just do module load OMFIT, and then we type OMFIT to start it. And then here we're going to import the step module. So here I can search. We're going to search for a step, and we're going to load it. And as you can see, STEP has a lot of dependencies in terms of the physics modules, which are all of the physics steps that we can run. So this is how the module is organized. Here we have all of the submodules that we just loaded. State is actually where we will have all of the data from our codes is going to be stored there, and it's going to be in this OMAS format. Let's see, under steps, these are the scripts that know how to run these modules. And these scripts basically know how to, are the ones that know how to load the data from OMAS, execute the module, and put the data back into OMAS. And then I should say that the step is a very flexible module in OMFIT. We can, because you have all of these physics components and you can run in any order, you can do these manually, or you can use some pre-baked workflows for the most common applications. So here under workflows, there are some common workflows that we've been developing and expanding. And this is what, for example, Tim will be using. So to start step, the GUI, we can double click. And here we are at the initialization phase. So here I should point out that we can initialize step in many different ways. And this is actually a good point to go to this slide and talk a bit about the initialization. So every step in our workflow exchange data through these ODSs, which stands for OMAS data structure. And step needs an ODS from which it can start its simulation. We call this the initialization step. What is contained in this ODS depends on what workflow you're running, but generally what you want is some equilibrium data, kinetic profiles, and then either the sources or the configuration of the heating and current derived actuators. And so step can be initialized in OMFIT in different ways. You can start from experimental data. For example, if you have done some kinetic equilibrium reconstruction with the kinetic time or cake. If you have existing simulations, for example, in TRANSP1-2 or actually even other transport solvers. From 0D parameters with Procreate, as Joe will tell us, or from data in IMAS databases. So for the purpose of this tutorial, the thing that would give us the best data in the shortest reasonable time was to start from a TRANSP simulation. And getting from a TRANSP simulation to an ODS requires a bit of steps. So I just want to lay them out here. So we have a TRANSP simulation in MDS Plus. We can run the TRANSP extract plasma state module in OMFIT. This will give us a state file and a G file. And then we have a GA code profiles preprocessor called profiles gen, which gives us an input J code. And then we have a method finally to go from this input J code format to an ODS. So now, if we go back to OMFIT, this is what we're going to do here. So we're going to go. We want to initialize step from profiles gen, and here we have two options. We can either load a new profiles gen module, or we can use one that is already here under tgyro profiles gen that is already this module. So we can just reuse that one, and then we can open the GUI of profiles gen. Here we want to start profiles gen from a state file and a G file. here, the user could provide a state file and G file, for example, a 1.2 state file and a G file or a transp state file. But we're going to use this TRXPL that I talked about. So now we're going to connect to MBS Plus and fetch this transp run. So here I have it already set up for the shot that I wanted. The time, we just need to add the right transp run ID that we want to get our data from. And we're going to use 100 millisecond averaging time. So if we click here, this is going to run this TRXPL code, which is in this module. When that is run under TRXPL output, we're going to see a G file, which we can actually plot, and a state file. The state file contains the data from transp. So, for example, just to show quickly, for example, TI. Okay, so this is the data that comes from transp. Now we can take these state file and G file, and we can generate the input GA code by running profiles gen. So here we've done this one. We're on TRXPL, state file and G file. We're running profiles gen to get the input GA code, and then from input GA code to ODS will be very quick. Okay. Again, this is a it is a bit convoluted, but that's the fastest way to get to an ODS from an existing simulation. Okay, shouldn't take too long. Okay, good. So under outputs, we now have this input GA code, and which again has the data. So, for example, TI, which I showed before, is still there. It also has information about the equilibrium. So once we have this input GA code, we can just click here, load ODS from module, and finally, step has this ODS that you can start working on. So under state here, we have state 0, which is our initialized ODS. Again, the data is organized according to the ITER format. So things are spelled out pretty clearly here. So we have the core profiles with the different time slices. In this case, where there is just one time slices, and you know, the data, for example, again, the electron temperature. There is the equilibrium here. I think this covers the initialization, and I'll pass the presentation to Tim. I think you're muted.
Yeah, that was some plane flying over here. Thank you for passing it over to me. Like as Orso already described, we now have our initial ODS in step, and now we're running this workflow here. And I'll be showing you how to run a workflow, like a pre-baked kind of workflow in using step. So again, we have you know, the screen that Orso showed. So we load the ODS into a module, and that will show us our big step GUI, which is pretty self-explanatory. Let me open also the tree here. We have here our ODS. So we can select the type of run. So this is the preset workflows. You can also go step by step. So make your own kind of workflow on the go. So we'll be running D3d upgrade, because we're going to explore some D3d shot. So we're going to look at the upgrades at an increased magnetic field. And we're going to run higher MBI power. So we're going to select that option here. It's all MBI no RF, because there was no RF in the shot. And a nice thing about these step GUIs is that we have an extensive help. So if you don't know, for example, what this does, you can click here. So here you see that this heating scenario is all MBI, which is 12 megawatts of co-beam, 2 megawatts of counter beam, and it has no RF. Next up, we set up the scan. So these are the scan settings. So we're going to look at 2 and 2.5 Tesla. We're going to run with cheese because we do not have information of the separatrix. We don't need to use a full EPET module because our EPET neural network in our T-gyro falls within the training data. We're going to do 2 full cycles. So 2 full cycles of this. That's what that means. We're gonna set up TGLF and with set 1 incremental. We're gonna evolve the rotation because we're gonna look at the beams. We're gonna do some current diffusion if it's drops below 0. So that's just as feasible with doing some experiments. And we're gonna use 1-2 for the current relaxation. So let me just quickly run this. This will take about 15 minutes per simulation. So we did 1 experimental run and then 2 predicted. So that will take time, but so we're not going to wait for this. So I already have some pre-baked solutions right here in this one. So this is what you will see when it finishes. You can see now that that our states are nicely filled from 0 to 7, and that also our RunDB has our experimental result and our 2 predictive simulations. So let's go over now to plotting to see what we actually have. So here we have our experimental result. So you can see the 0 is initialization, and we have cheese 1, 2 T-gyro. And as you can see, we start off with some profiles in Equilibrium. And then 1, 2 adds the core sources. And then T-gyro adds the core transport. And then so on and so forth until we get to the final solution. So let's quickly compare how our experimental results compare. So for that, we plot we select the 2, we plot the core profile. As you can see, the results are pretty accurately matching between the 2. The only important thing that we're not having implemented yet is to use some fast ion diffusion in Freya. As you can see, the core densities are a bit oversaturated. And a more robust way is being worked on by Joey that matches, for example, the beam thermal neutron fluxes, so that you have a diffuse heating profile. But the rotation and all the other things matches pretty well. So that gives us the confidence, to do our predicting outwards. So let's look at those results now. So these are stored here. So we could, put them in here and then look at them, one by one, or we can use a different plot mode called compare RunDB individual. So here you have all of them together. So let's select our experimental case here, which would be the initialized from the experimental, the final result that we had there, and the two predictive runs. At high field, the last one, and let's also select the lower field, but same MBI. And let's first look at some core profiles. Let's see if these results make sense. So let's see, the blue one is the experimental one from trans. Then we have the green one that was slightly overfitting in the core. And then we have the 2 predictive one where we can see higher field gives higher density, that makes sense. And increased NBI power gives higher ion temperatures compared to electron temperatures. And rotation increases as well based on increased NBI power.
One thing to say, Tim, is that when you scale the magnetic field, you also scale IP, and you also scale the electron density. So to keep the Greenwald fraction constant, right?
Yes, that's correct.
So that's why the higher field has
Higher density.
It's not, yeah, it's yeah.
Mm-hmm. Yeah. So that's more or less what I wanted to show. We can also take a look at, for example, if you're at the ODS, you can right-click it, and then you have some plotting method based on what's inside. So, for example, this is the last experimental run. We can see the core transport fluxes, for example. So this is really what Tijaro is doing, where you can see the temperature, the profiles on the left, and then the heating sources, and how well NEO and TGLF matches the model targets. And in this case, Tijaro converges pretty easily. Yeah, so that's just what I really wanted to show. I mean, I can also show that it's still running here, and our RunDB is slowly being filled. And other than that, I want to give it to Joey that's going to look at some reactor simulation using Procreate as an initialization.
Yeah, sure. So let me share my screen. So I'll just do my no machine. Okay. So you can see my screen now?
Yes.
Okay. Okay, so we're gonna just delete that. Okay, so I'm gonna basically just try and design a reactor from scratch with just very simple 0D parameters. And so to do this, we're going to start with what's called the Procreate module. And so it's short for profile create. And so the Procreate module can basically generate realistic initial starting profiles for the step modeling. And so we're going to open up the Procreate module. And so we're going to start from just 0D parameters. So we're going to, in the start from option, we're going to click 0D parameters. And then in Procreate, we're also going to give, are going to set up some initial just Gaussian heating profiles. So we'll click set up Gaussian heating profiles. And this is done through the OMFIT Chef module. Chef stands for current drive heating and fueling. And so it can do various current drive and heating schemes, but we're going to look at the most basic, which is just a Gaussian heating and current drive profile. So we're going to load Chef. Okay, let's see. Here it shows all the codes Chef is capable of running. So it's loads up Rabbit, Pam, Freya, Tori, and Genray for calculating heating. All right. So
PAM is a pellet ablation, right? Pellet ablation module.
Yeah. PAM is a pellet ablation module, so it can include effects from pellet ablation. Okay. So we're going to choose to look at an H mode plasma. So we're going to use H mode profiles, and then we're going to, in Procreate, we're going to set up the current profile so that it can matches the bootstrap current. So by clicking this button, it'll do that. And then we're just going to set up an initial reactor. So we're going to choose, say, an 8 megaamp, 8 Tesla reactor, and choose a pedestal width of 0.04. That's pretty standard. And then we'll choose a pedestal to be, let's say, 4 keV pedestal. And then we'll take a pedestal density to be, I mean, this value should really be chosen based on the Greenwald fraction. And so for this case, I'll choose it to be 0.8. And on-axis temperature of around 21 keV, and core density of maybe 1.3 or so. Just leaves the effective as 2, And then I'll reduce, since this is a reactor, we probably won't have neutral beams, so we'll just reduce the rotation down to 10 kiloradians per second. And then, so this is kind of just the 0D initial temperature and density profiles, and then we also need to set up the shape. So to do that, we'll then go to the shape type, and we'll click on interactive boundary shape, and we'll just specify a minor radius to start with. It helps the interactive GUI plotting be a little bit better. And then we'll click modify shape, and it'll give us an initial plasma. And so this has a minor radius of 1.5 as we input over there, aspect ratio of 3. So just kind of parameters that are similar to the D3d tokamak, but with a minor radius of 1.5. So if we wanted to say simulate a 4-meter tokamak, we would then just reduce the radius to minor radius to 1.333. And then just for, I don't think this really matters in terms of the actual T-gyro predictions, but I personally like to just make the outer squareness to be slightly negative. It makes it give it a slightly better or closer to the experiment triangularity shape that you usually see. So this is initial shape that we'll take. So it's a 4-meter tokamak with elongation of 1.8, both upper and lower, and triangularity of 0.6. And then we'll have to set up then our current drive and heating. And so to do this, we'll use a heating source type as just some Gaussian sources. And we'll set up a template just based on this, what's called the general Gaussian template. And we'll switch to this. And so we added that template. And so I added this template as the 0th source. And so we'll click on the 0th source, and it'll give us some options for the heating and current drive source. One thing is you specify a radial location and then the Gaussian width in normalized row space. And then you can specify a particle source, heating sources to the electrons and to the ions and to the and then a current drive source. And so for this case, we'll choose say 30 megawatts to the electrons and 30 megawatts to the ions, and then say 1.5 megaamps of current driven. And then with all these things set up, then we can just click run Procreate. And Procreate will generate profiles based on all these parameters you chose to set up. And so it'll take a few minutes because it has to run IMAS a few times. Are there any questions about maybe the Procreate part? Oh, that's new. Oh, okay. That was my mistake. Forgot to set up a Equilibrium solver because we're doing everything just from 0D. You can't use IMAS because you don't have the coils set up. So you have to run with the cheese Equilibrium solver. And then we'll try running it again, which I don't understand why this happens in OMFIT. Well, we'll reload the module and then run Procreate.
So Chris was asking if the ions should be DNT.
Oh, yeah.
Probably DT with helium, right?
Thank you.
Gonna get this.
Skip that too. Okay, yes. So we can use, thank you, Chris, you catching my mistakes. So yeah, so we need to we should use ions. Since we're trying to design a reactor, we should use ions with deuterium and tritium. And we use just deuterium, tritium, helium, and neon for the impurity species. And it did it again. Don't understand. Okay, well, if your button disappears, you can just reload the module and run Procreate.
The one thing I noticed is that in your heating and current drive, you have a button to preview the sources.
Oh, thank you. And I'm going to stop it again because we should preview sources. It probably is fine to preview the sources. And so this source is actually pretty peaked, probably too peaked. So you can, if it's not to your liking, you can increase the width of the source, and then it'll be perhaps a more realistic, slightly more realistic profile source.
Third time is charm.
Hopefully. Okay.
Then maybe I can read some of the questions that have been made. Tomasz was asking if STEP is good for time-dependent simulations. And right now, STEP is not set up for time-dependent simulations.
Mm-hmm.
We have some ideas on how to extend it to time-dependent simulations. What I should say is that the ITER data structure supports time dependence. So it's effectively just a matter of orchestrating the physics steps to be run for different times, and perhaps do it in a computationally efficient way. So that's something that we're considering, but and the way things are set up does not preclude us from do this in the future.
Okay, great. So now our Procreate simulation finished, and okay, well, and now we have some buttons at the bottom, so you can preview the Equilibria, and it shows us what our initial. So the green Equilibria is here. So what Procreate did is it first generated some Equilibria for to run cheese, and then the second Equilibria is the adjusted Procreate Equilibria with your desired pressure profile and also your Q profile. And then you can also preview the initial core profiles, which are given as we specified. And you can also plot your heating profiles too.
And really the point here is to make some profiles that are physically plausible. We know that they're not self-consistent, and that's why we start from these things, and then we will run STEP, right?
Yes, exactly. So these are just giving you some initial profiles so that you can run STEP. Okay, so now we open up the STEP GUI, and so in this case, instead of running from the G file and the state file, we're going to just load straight from the Procreate module. So that'll load up the ODS. And so then, similar to what we were doing, or what Tim did, you could run this preset workflow. And so you can run the standard workflow, but maybe we want to do something before that. So what we could do is, instead of doing preset workflows, we could do a custom single step. And we might want to run EPED first so that you have a realistic boundary condition, especially for a reactor where we kind of just guessed 4 keV for the pedestal. Now, just for time's sake, we'll we'll use EPED neural net, though this EPED neural net's not really trained for this reactor, so be careful about when you use it, but just for speed, we'll use it, but ideally you'd be using the full EPED if you're running this for a reactor. So then what we can do is we can then, there's kind of, in this custom single step, there's three different things you have to do. First, you set up EPED to run, and then you would run EPED, and then you can save it as the next state. So I just set up EPED to run based on the initial ODS, and then I would run EPED, and since I have the checked EPED neural net, it should just run the EPED neural net. And
perhaps, Joey, can you show the state in the OMFIT tree, just as you're doing this?
Okay, sure, yeah, and then we can save this EPED result as state 1, and then you want to show me the and so then in the OMFIT tree, there's a OMFIT tree called state. These is where your ODSs are saved. The 0th one would be the one we started with from Procreate, and then the one state would be this EPED state we just ran.
Yeah, perfect.
Yes. And so we can actually see, so if we go into the ODS and look in summary, you can actually see what your pedestal is. So for state 0, it had a pedestal of 4,000 keV. And if you look at 1, then it updated it to 6,300. How realistic that is, maybe not, because this is EPED neural net where it's not trained, but ideally you'd be running with the full EPED if you're running this type of plasma. Okay, and then with the initial condition, then you could go back to just doing a preset workflow, and you could run, say, 1.0, the standard equilibrium heating and current drive and transport workflow. So this is the workflow that Orso was showing at the beginning of this tutorial, and then you could set it up to be all the parameters you want. And I think I already set this one up, unfortunately. So you would choose, say, the equilibrium code to be cheese, as is necessary. You would use a chef module to update your heating, and then run maybe two cycles of the workflow, and then you could evolve the pedestal with EPED neural net and tgyro if you liked, or you could keep it fixed. And then you could run various tglf and tgyro options, such as evolving the rotation, various tglf roles such as electrostatic or electromagnetic. You can add current diffusion to make sure your current profile doesn't drop below 1. And then in this case, we also set turned off 1.2 and 1.2 ECH and 1.2 beam models, as we just are the only heating source our auxiliary heating source we're gonna have is this chef heating source we set up initially. And so with all these things set, you could just run this workflow, and tgyro takes a lot of time because when it's simulating a reactor, so instead of waiting for this result, you can go to just one that's been already run.
And actually, maybe Joey, as a comment, that in the step GUI, we just show some of the most commonly used options, but each of the physics module has many more options, and if necessary, every single parameter that is in the name list of the physics codes could be adjusted.
Yes, absolutely. But those are the ones that are been typically adjusted by the people that are currently using STEP. And yeah, there are other terms that other people like to adjust, then maybe we should add them into the GUI too. But also, even if they're not in the GUI, you could change them in the individual module and they will just stay fixed. And so you can, so we have this pre-cooked solution, and you can look at then the final core profile. Yeah, so we can then compare these. And, so we can compare the equilibria starting from procreate and ending. And so we can see the Q profile changed significantly, and the predicted pressure profile changed with, let's see, yeah, green being the T-gyro simulation and blue being the initial starting profiles. And you can also plot the core profiles, and shows how the core profiles change. So it looks like the pedestal is a little bit higher for the step simulation, and then the gradient scaling is lower. And then you can also do a print summary, which will show you a lot of the summary data from the step simulation. So it'll show you pedestal information such as the temperature and density. It'll show you your confinement time, your neutron rates, and your fusion power. So this specific case only got to a fusion power of 226 megawatts, unfortunately. And then there's other things such as your plasma currents, your non-inductive currents and ohmic current, your Greenwald fraction, and also your major radius, BT, beta N, and so on. All right.
Okay.